Alright, in this video I'm going to demonstrate a graphical solution to a horizontal launch. When you read the question, the trick is always to extract as much information as you can before sketching and drawing. We're told that the launch is horizontal, we're told that the building's 40 meters tall, and the initial velocity is 30 meters per second. First thing we do is we always make a well-labeled sketch, and then once we do that, then we can start looking at what we're being asked to solve. So I'm on a building that's 40 meters tall. My ball is located at the top. I'm going to label this x0. The ball's going to land somewhere right around here. I'll label that xf. It's usually a good idea to trace out the trajectory as close as you can. Now we're going to label some vectors. For free fall, this one's kind of straightforward. The acceleration vector points straight down, Galileo's constant. The displacement is a straight line separation distance from start to finish. Don't forget to add the little arrow. The velocity vectors are sometimes tricky. We're told it's a horizontal launch at the start. And to draw the final velocity, you just kind of have to trace the trajectory and just kind of do a best guess. It doesn't have to be perfect, but like I said in the last video, many questions on the AP test are just asking you which way is it pointing at the end. And so you can, with a well-labeled sketch, solve this. All right, now in question A, it's asking how much time is it in the air. That doesn't really show up on a sketch because it's not something you can see. It's something that is time, of course. The range of the ball is a special vocabulary word in physics. The range is just the horizontal displacement from start to finish. Where did it land compared to where did it start? And I like to call that the displacement in the x direction. And then letter C is asking what's the final velocity. It wants an angle and also a magnitude of the speed. Alright, the first thing I'm going to do is I'm going to deconstruct the initial velocity. In this case, my original speed was 30 meters per second. And in the y direction, it's going to equal 0. It's a horizontal launch. And so in the x direction at the start, 100% is equal to the x motion. Now if it's a horizontal launch, theta equals 0, and you can do the sine and cosine to get those values, but you don't really need to in this case. Now that I have my graph, I'm going to, or my velocity vectors in each dimension, I'm going to make my velocity versus time graphs in the x and y direction. Oops, mistake. My velocity in the x direction versus time, and my velocity versus time graph in the y direction. Alright, as we saw from our projectile motion lab, in the x direction, my starting velocity is constant throughout. So as long as that ball's in the air, it will be traveling 30 meters per second. In the y direction, my velocity at time equals 0 is 0. And it is also subject to Galileo's constant, which I'll say is -10 in this case. Okay, now I need to figure out the time that the object's in the air. That is easiest done in this case by figuring out how much time it takes for this object to lose 40 meters. So the displacement in the y direction is equal to -40. And so this triangle right here will be the time interval that it's in the air. This right here is my final velocity, but that is also equal to a times delta t. And so to solve for the time, I'm just going to use the area of that triangle. Negative 40 is equal to 1/2 times delta t times VF. The VF doesn't really do me any good, and so I'm going to substitute A times delta t plus 0 in this case in for VF. So my formula is negative 40 equals 1/2 times negative 10 for Galileo's constant times delta t squared. And then when I solve that for delta t, delta t is going to equal the square root of 8, which is approximately equal to 2.83 seconds. And that's the answer to letter A. Solving for time is basically solved like this every time, although when it's an angled launch, it's a little more complicated. Now, as soon as I figure something out, I'm going to add that to my graphs. Now, an interesting thing is that time is what's common between the x and y graphs. It's the same clock reading when it hits the ground, no matter which dimension you're looking at. And lo and behold, I have just dimensioned out this rectangle right here. This rectangle right here is the displacement in the x direction, which is going to equal 30 times 2.83, which is equal to 84.9 meters. And that's the answer to letter B, the range. The final question is asking what's the final velocity vector. And what I have to do here is I have to take the final velocity in the y direction, the final velocity in the x direction, and I need to reconstruct my velocity vector. I kind of did the exact opposite at the start, but now I need to put it back together. So in the horizontal direction, my velocity is constantly 30 meters. And that's VF in the x direction. VF in the y direction takes a little bit of work. But here's what I know. I know that because it's in the air for 2.83 seconds, and that it's losing 10 meters per second, for every second, that it's going to lose 28.3 meters per second total. You can plug these values into this equation if you want and get the same thing. Now, what I can do is I can use the Pythagorean theorem to figure out what the hypotenuse is of that reconstructed triangle. And I've already done that. It's equal to 41.17. Okay, and that's in meters per second. Ooh, my units are sloppy today. To figure out the angle, always with respect to the horizontal, theta is going to equal the inverse tangent of opposite over adjacent. And when you plug that in, you're going to get theta is going to equal negative 43.23 degrees. And that negative just means underneath the horizon. Make sure you're in degree mode when you do that with your calculator. And there you go, horizontal launches.